Now, let's break down Lora, low-rank adaptation, and how it works for fine-tuning large pre-trained models in a way that's both efficient and effective. Let's explore it in 4 parts. Lora model architecture and core concepts. How does the rank parameter affect the performance of Lora models? How does Lora handle style specialization in image generation? How Lora apply to image generation and language models? Let me discuss Lora model architecture and core concepts. The core idea behind Lora is to fine-tune models by updating only parts of the model rather than adjusting every parameter. To achieve this, it uses something called low-rank decomposition. Essentially, instead of updating the entire weight matrix, which could be huge, Lora breaks it down into 2 smaller matrices that require less computation and memory. The first, architecture components. 1. Original weight matrix W. The starting point is the original weight matrix W, which holds the parameters of the pre-trained model. This matrix stays frozen, meaning it doesn't change during the fine-tuning process. 2. Update matrices, A and B. Lora introduces 2 new matrices, A and B, that are much smaller than the original weight matrix. These matrices are the key to making Lora so efficient. Matrix A has dimensions of R multiply D. Matrix B has dimensions of D multiply R. Here, D is the original dimension of the weight matrix, and R is a rank parameter. This rank R is usually much smaller than D, which allows us to reduce the number of parameters to train. 3. Low-rank approximation. The update to the weight matrix W is approximated by multiplying matrices A and B. W equals A multiply B. This approximation drastically reduces the number of parameters we need to update, making the fine-tuning process more efficient. The second, training process. The training process in Lora works like this. 1. Initialization. Start with the original model's parameters, W frozen. 2. Training. Fine-tune only the new matrices A and B. These are the only parameters that will change. 3. Inference. When making predictions, the final output combines the original model weights with the updates from matrices A and B. Here, X is the input to the model, and H is the final output. The third, key features of Lora. 1. Reduced parameter count. Lora greatly reduces the number of parameters you need to train. For example, instead of working with a large 200 multiply 200 matrix, which has 40,000 parameters, you can use 2 smaller matrices, one of size 200 multiply 2, and another of size 200 multiply 2, 2 multiply 200. This results in only 800 parameters to update. 2. Adaptability. Lora doesn't have to change the whole model. It can be applied to specific layers or modules. For example, in models like Stable Diffusion, it often targets the cross-attention layers. 3. Rank parameter, R. The rank R is a key factor. The smaller the rank, the fewer parameters to train, making the process faster and more efficient. But setting it too low might affect model performance. 4. Scaling factor. Lora also applies a scaling factor to the output of the product of A and B. This is typically set to alpha divide R, where alpha is a hyperparameter, often set equal to the rank R. The fourth, advantages of Lora. 1. Memory efficiency. Because you're only training a small number of parameters, Lora uses much less memory. Unlike full fine-tuning, which requires storing the entire fine-tuned model, Lora only needs to store the smaller rank decomposition matrices. This drastically reduces the memory and storage requirements. 2. Faster training. Fewer parameters mean faster adaptation to new tasks. Lora only trains model parameters between 0.5% and 5%, compared to about 100% for full fine-tuning. In some cases, Lora reduces this to as little as 0.01% of the original model's parameters, making it incredibly parameter efficient. 3. Hardware accessibility. Lora makes it possible to fine-tune large models even on hardware that might not have been able to handle the full parameter set. 4. Modularity. You can swap Lora adapters in and out of the model, adding specialized capabilities without needing to change the entire model. The fifth, considerations for implementation. 1. Target modules. When using Lora, it's important to decide which layers of the model to apply the low-rank adaptation to. For language models, this often involves modifying the query and value projections in the attention layers. 2. Initialization. Lora weights can be initialized using methods like loft-q to improve optimization. 3. Integration. To add Lora to an existing model, techniques like graph rewriting can be used. This has been demonstrated in frameworks like Axon. In summary, Lora makes it easier and more efficient to fine-tune large pre-trained models by reducing the number of parameters that need to be updated. This allows researchers and developers to apply powerful models to specialized tasks without needing massive computational resources. It's a great solution for adapting AI models with more limited hardware while still achieving good performance. Let's discuss the role of the rank parameter R in Lora models and how it affects both model performance and computational efficiency. The first, impact on model capacity. For higher rank R, more capacity. A higher rank allows the model to capture more information and patterns, which enhances its ability to adapt to specific tasks. Better performance. This can lead to improved results on complex tasks because the model can capture more nuanced details. For lower rank R, fewer parameters. A lower rank results in fewer trainable parameters, which leads to faster training and reduced computational requirements. Potential trade-off. However, it may limit the model's ability to capture certain task-specific information, especially for more complex tasks. The second, performance trade-off, accuracy and efficiency. Higher ranks improve accuracy, but increase the computational load, making training more expensive. Lower ranks speed up training and reduce resource use, but may cause a performance drop if set too low. The third, empirical observations. 1. Performance plateau. Studies suggest that increasing the rank beyond a certain point doesn't lead to significant performance gains. For example, ranks above 8 or 16 might offer diminishing returns in many cases. 2. Model size. The impact of the rank parameter can vary depending on the model's size. Larger models may benefit more from higher ranks because they have more capacity to handle additional parameters. The fourth, practical recommendations. 1. Experimentation. It's important to experiment with different rank values to find the right balance for your specific task. A common approach is to start with lower ranks, for example, 8 or 16, and gradually increase if necessary. 2. Task-specific tuning. The optimal rank depends on the complexity of the task and the dataset. Some tasks may require higher ranks, such as 32 or more, to achieve optimal performance. In summary, while higher ranks generally improve model adaptation and performance, the benefits may plateau after a certain point. The best rank value depends on the task, model size, and computational resources, so it's essential to fine-tune the rank through experimentation for each specific use case. Then, let's discuss how does Lora handle style specialization in image generation. Lora, low-rank adaptation, is a powerful tool for style specialization in image generation, enabling large pre-trained models like Stable Diffusion to adapt to specific visual styles or themes with high efficiency. Let me break it down for you. The first, efficient fine-tuning. Lora allows us to fine-tune large models quickly and with minimal computational resources. Here's how it works. Low-rank matrices. Lora introduces low-rank matrices during the training process, significantly reducing the number of parameters that need to be updated. This keeps the process computationally efficient. This approach allows us to adapt models to new styles or themes without the need for extensive retraining, saving both time and resources. The second, style-specific training. To specialize in a particular style, Lora models are trained on smaller, targeted datasets. Users can create custom Lora models by training them on a relatively small set of images, about 5 to 10 for specific subjects, or 20 to 100 images for styles. This allows the model to pick up the specific visual characteristics associated with the desired style, enabling it to reproduce those features in generated images. The third, dynamic adaptation. Recent improvements in Lora have introduced more dynamic methods to handle style adaptation. Style inject. This approach uses multiple parallel low-rank parameter matrices. Each matrix adapts to different visual features, making the model more flexible in terms of style handling. The model adjusts its adaptation based on the input, ensuring that it can vary the visual features while preserving the core semantic accuracy of the image. The fourth, integration with base models. Lora can work alongside base models like Stable Diffusion. Lora acts as an add-on or adapter, which can be easily integrated into the main model. This setup allows users to apply specific styles to a wide variety of subjects, even those not originally part of the base model's training data. The fifth, combining styles. Lora offers even more flexibility by enabling the combination of multiple styles. You can combine different Lora models, blending artistic styles or themes to create unique outputs. Tools like Lora Composer help users merge concepts from different models, using textual and layout cues to guide the synthesis of images with complex multi-style combinations. In summary, Lora's approach to style specialization is both flexible and efficient. It allows users to customize and generate images in highly specific artistic styles, all while maintaining the original model's core capabilities. Whether you're focusing on a single style or blending multiple themes, Lora provides the tools to do so in a computationally efficient manner. Then, to understand the underlying principle of Lora, low-rank adaptation, in the context of Stable Diffusion and large language models, let's break it down in terms of how Lora applies specifically to both domains, while also highlighting the general principle of Lora. Let me discuss Lora in the context of Stable Diffusion. Stable Diffusion is a text-to-image generation model that uses a UNet architecture along with a text encoder, CLIP, to generate images from text prompts. The model involves self-attention mechanisms in its UNet to process the relationships between different parts of an image or between text and image features. Lora adapts this model without retraining the entire UNet or encoder, making it computationally efficient. 1. Low-rank matrix adaptation. Lora applies low-rank matrices to the weight matrices in the attention layers of the UNet architecture. Specifically, it targets the query, key, and value matrices used in self-attention, which are the primary components responsible for learning relationships in the image generation process. Rather than updating the entire weight matrix, which could have millions of parameters, Lora introduces low-rank modifications, represented by matrices A and B, which are much smaller and computationally cheaper to train. These matrices capture the task-specific knowledge such as image style or artistic transformations. For the mathematical formulation, instead of updating the original weight matrices directly, Lora adds a low-rank update, where W is the original weight matrix in the attention layers. A and B are low-rank matrices that are trained during the fine-tuning process. The final W is the updated weight matrix used during inference. 2. Task-specific adaptation. When fine-tuning Stable Diffusion with Lora, only the low-rank matrices A and B are learned, while the rest of the model's parameters, such as the original attention weights, are kept frozen. This allows Stable Diffusion to specialize in a particular domain, such as specific artistic styles, without needing to train the entire model. For example, you could adapt Stable Diffusion to generate images in the style of a particular artist or genre by training only the low-rank matrices. 3. Parameter efficiency. Lora significantly reduces the number of trainable parameters, making it possible to fine-tune large models like Stable Diffusion in a more memory-efficient and time-efficient way. This is particularly beneficial for applications that need to adapt the model to new domains or styles without consuming vast amounts of computational resources. Then, let me discuss Lora in the context of large language models. LLMs, such as GPT, Generative Pre-trained Transformer, and T5, text-to-text transfer transformer, are built on transformer architectures, where self-attention mechanisms are used to model relationships between words or tokens. Lora can be applied in a similar way to these models as it is to Stable Diffusion by introducing low-rank updates to specific layers, like attention layer. 1. Low-rank updates in attention layers. LLMs like GPT use self-attention to capture dependencies between different tokens in a sequence. Lora applies low-rank modifications to the query, key, and value matrices in the attention layers of the model. Just as with Stable Diffusion, the goal is to adapt the attention mechanism to task-specific knowledge, for example, sentiment analysis, translation, by learning only the low-rank matrices, not the entire set of model parameters, for the mathematical formulation, where Q, K, V are the original query, key, and value matrices in the attention mechanism. AQ, BQ, AK, BK, AV, and BV are the low-rank matrices that will be learned during fine-tuning. 2. Task-specific fine-tuning. Fine-tuning an LLM with Lora involves updating only the low-rank matrices, A and B, while leaving the rest of the model parameters frozen. This allows the model to specialize in certain tasks, such as sentiment classification or specific domain knowledge, without retraining the entire model from scratch. For example, if you want to fine-tune GPT for medical text generation, you would train the low-rank matrices to adapt the model's language generation to that domain, while the rest of the model remains unchanged. 3. Parameter efficiency. Just like in Stable Diffusion, applying Lora in LLMs reduces the number of trainable parameters significantly. Instead of updating billions of parameters in the original model, you only need to train the smaller low-rank matrices, A and B, making the process computationally more feasible and efficient. 4. Specialization for different tasks. Lora allows LLMs to be specialized for different tasks, such as summarization, translation, question answering, or domain-specific tasks like law or medicine, by training different low-rank adaptations for each task. You can effectively have a single pre-trained LLM that adapts to multiple tasks by learning different low-rank matrices for each specific task or dataset. In summary, in both Stable Diffusion and LLMs, Lora leverages low-rank factorization of the model's attention weights, or other key layers, to achieve task-specific adaptations. This approach allows the models to specialize in new domains or tasks efficiently without the need for expensive full-model retraining. The underlying principle is to use low-rank matrices to add the required task-specific knowledge, while leaving the majority of the model's parameters unchanged, making the process more efficient both in terms of memory and computation.